Scientists using the James Webb Space Telescope are staring at a dim red star about 124 light-years away and arguing over a handful of bumps in a spectrum. Around that star orbits K2-18b, a sub-Neptune world larger than Earth but smaller than Neptune, probably wrapped in a thick hydrogen atmosphere above a deep global ocean. When Webb watches the planet pass in front of its star, some of that starlight filters through the atmosphere and picks up the chemical fingerprints of whatever gases are floating there. Those fingerprints are the reason anyone is whispering about alien life. In 2023 and 2024, analysis groups looking at Webb's early data found methane and carbon dioxide in K2-18b's atmosphere. Exactly the kind of mixture you might expect over a warm ocean world. Buried in one part of the infrared spectrum, one team thought they saw something even stranger. A pattern that looked like dimethyl sulfide, a molecule on Earth mostly produced by marine microorganisms near the surface of our oceans. If that identification were ironclad, it would be the first time a possible biological gas has been seen on a world orbiting another star. The problem is that nothing about that signal is ironclad. Different teams run the same spectrum through different calibration pipelines, subtract different models of Webb's own instrument noise, assume different cloud heights and atmospheric temperatures, and get slightly different answers. One group's dimethyl sulfide feature is another group's modeling artifact. Nobody disputes that K2-18b is interesting and probably wet. The argument is whether the current data justify claiming any specific biosignature molecule at all. That disagreement is what mature science looks like at the edge of a new tool's capability. Webb was designed first as a general infrared observatory, not a dedicated life detector. It looks at a star system for a few transits, not hundreds. It has to share time between exoplanets, the first galaxies, star-forming regions, and the dust around dying suns. The result is that for a planet like K2-18b, scientists are trying to squeeze decisive answers about life out of data sets that were barely possible 10 years ago and still sit right at the instrument's noise floor. From the outside, that nuance tends to get flattened. One headline shouts that we have the strongest evidence yet of life beyond the solar system. Another insists the whole thing is hype and that Webb has found nothing but hot hydrogen. The reality is far less dramatic and far more interesting. The tools are working, the community is testing every claim until it breaks, and over the next decade, the statistics on many planets will slowly harden from maybe toward probably or no signal at all. While that quiet argument plays out on the scale of light years, a different kind of problem is building just a few hundred kilometers over our heads. The International Space Station has been continuously inhabited since the year 2000, an orbital construction made from Russian, American, European, Japanese, and Canadian hardware and budgets stitched together. It was never meant to last this long, yet because it has become familiar, a moving dot you can find from your backyard with a phone app, people often assume it will simply keep circling until someone remembers to bring it down. Engineers do not get to assume that. For them, the station is not a symbol, but a steel and aluminum pressure vessel that has been cycling between hot sun and deep cold 16 times a day for decades. It has endured micrometeoroid hits, thruster firings, unplanned power losses, coolant leaks, and the wear of thousands of human hands and tools. Every weld, hatch seal, and cable run that was signed off in the late 1990s has now lived through years of vibration and stress beyond its original test campaign. The most worrying problems today are concentrated in one place: the Russian-built Zvezda service module. Its structure dates back to the mid-1980s, when it was assembled as a backup for the Mir program, and it finally flew to orbit in 2000 to become the living and propulsion hub of the station's Russian segment. At the back of Zvezda is a short transfer tunnel that leads to a docking port used by cargo ships. Since 2019, that little vestibule has been slowly leaking station air into space through microscopic cracks in its shell. At first, the leak rate was so small that it barely dented the station's supply margins. Over time, it has grown to the point where, unmitigated, it would vent several pounds of air each day. That is still manageable as long as visiting spacecraft keep bringing fresh tanks of nitrogen and oxygen, and the crew keep the hatch to the vestibule closed whenever they are not using it. But it is a clear sign that some combination of weld quality, design geometry, and mechanical fatigue is now catching up with metal that has been hammered by temperature swings and micro vibrations for decades. No one on board is in immediate danger. The crew can isolate the leaky space, monitor pressure, and respond quickly if it changes. The concern comes from what happens when you look forward 5 or 10 years. Probabilities start to stack. An old module that is already cracked will keep aging. More micrometeoroid impacts will accumulate. Valves, pumps, and cables across the whole station will keep getting older, and budgets on the ground will always be finite. Safety panels inside NASA have started to describe this interval, from now to the planned retirement around 2030, as the riskiest period in the station's life. Risk here does not mean guaranteed catastrophe. It means that in the simulations, more runs end in ways the agency does not like. Engineers feed in models of structural fatigue, impact rates, software faults, and human error, then run thousands of synthetic futures to see how many of them still allow a controlled deorbit, how many require emergency evacuations, and how many lead to fragments falling in the wrong places. As margins shrink and systems age, the curves get steeper. That is why NASA has put serious money into a dedicated deorbit tug, a one-time spacecraft whose entire job will be to grab the ISS at the end of its life and push it into a targeted dive over open ocean, instead of letting an uncontrolled breakup spray hardware across populated regions. The ISS story is not just about avoiding bad endings, it is also about buying enough time for whatever comes next in low Earth orbit. NASA wants private companies to build and operate future stations, with the agency as an anchor customer instead of the owner of every bolt and hatch. That transition is not as simple as handing over a set of keys. Commercial stations will still host national astronauts, carry out sensitive research, and maybe even support defense or intelligence payloads. Space law, insurance frameworks, crew certification standards, debris rules, and rescue obligations all have to be rewritten for a world where a company, not a space agency, runs the habitat. That is why some former NASA managers are nervous. If the ISS has to be abandoned early because of a structural issue before the commercial stations are ready, the United States could find itself without a continuous human presence in low Earth orbit for the first time in decades. On the other hand, if the agency keeps pouring money into patching aging modules long after it makes engineering sense, every dollar spent on emergency welds is a dollar not available to help industry design safer replacements. Far from the space station, in a desert test site, another company has already learned the hard way how brutally reality can judge hardware. SpinLaunch spent years developing and promoting an orbital launch system based on a giant vacuum centrifuge. The idea is simple to explain and difficult to execute. Spin a projectile up to several times the speed of sound in a sealed chamber, and release it through a nozzle so that it punches through the atmosphere on pure kinetic energy, then light a small rocket engine at the top of the arc to finish the trip to orbit. Most of the launcher stays on the ground, ready to spin again. On paper, the advantages are obvious. The reusable ground hardware does almost all the work. The rocket that actually flies is much smaller and cheaper than a typical orbital booster. For small satellites that can handle high acceleration, the cost per kilogram could in theory drop sharply. SpinLaunch even built a 1/3 scale accelerator and fired test shots, proving that the basic mechanical concept could survive repeated runs without shredding itself. Scaling that machine to orbital velocity is an entirely different challenge. The full-size launcher would have to fling payloads at speeds far beyond the tests, withstand violent forces in its own structure, and convince both regulators and customers that delicate electronics and optics could survive the launch environment. Every notch higher in spin speed multiplies the engineering difficulty. Money follows risk, and investors eventually started asking when the company would generate revenue instead of just dramatic footage. The current answer is Meridian, a conventional low Earth orbit broadband constellation. Instead of betting everything on its exotic launcher, the company is now ordering a fleet of a few hundred small satellites from an established manufacturer and planning to loft them on traditional rockets. The constellation is meant to provide connectivity to large customers on fixed, predictable orbits, with the added promise that someday, if the accelerator does mature, spin launch will be its own best customer and can tilt launches over to its in-house system. Seen together, K2-18b, the ISS leak, and Meridian are three views of the same discipline. In each case, physics sets the outer limits. Telescopes can only collect so many photons from a distant planet. A pressure shell in orbit can only survive so many thermal and mechanical cycles before cracks appear. A spinning launch arm can only reach certain speeds before structural margins collapse. Within those boundaries, people make choices about how honest to be with the data, how long to stretch hardware beyond its design life, and when to retreat from a glamorous concept to a practical compromise that actually pays for itself. The narratives that reach the public rarely reward that honesty. A claim of alien life travels faster than a careful paper saying the signal is not yet convincing. A heroic image of astronauts floating in a sunlit cupola is more shareable than a graph of leak rate versus time for an aging hatch. A video of a prototype projectile blasting out of a centrifuge generates more excitement than a contract announcement for a standard batch of communication satellites. But in the long run, the work that matters is in the margins. The calibration notes, the inspection photos, the failure reports, and the budgets that match what the engineers say is necessary. What will actually shape the next 20 years in space is not the noisiest claim, but the quiet ability to say, "We do not know yet," or "This structure has reached the end of its safe life," or "The ambitious version does not close, but this simpler one does." The James Webb teams wrestling over Spectra, the station managers scheduling weld inspections around crew sleep, and the launch startup executives pivoting from a dream machine to an ordinary satellite fleet are all practicing the same craft. They are learning where the real edges are and adjusting before those edges cut them. In that sense, the real story is not whether K2-18b hosts some hidden ocean biology, whether the International Space Station limps all the way to its planned retirement date, or whether an orbital centrifuge ever makes commercial sense. It is whether the people running these projects keep choosing measurement over wishful thinking, controlled endings over graceful decay, and working compromises over plans that never leave the whiteboard.